Hello teachers and technicians. So this video is really about ways that you can measure the acceleration due to freefall. Now this can start off really simply where you just get a ball and you hold it, then you drop it and you record the time it takes to reach the ground. Now of course there are going to be lots of errors and ways that that method can be improved. And I think that's why this is a really nice experiment, because we know the value that we're trying to get to. We're trying to get to 9.81, and it's a good way to compare different methods that are used to get to the same end result. Now I do have a guide for students with some stuff for teachers at the very end. I talk a bit about the theory, and in this guide I go through a few different methods. The first one is the falling ball method, the kind of standard trapdoor method, and I'm going to show you a setup of some equipment that I found works really well. The second method you could use would be using light gates. Again, you can have a falling object, and in this case it might be either a combination of 1 or 2 light gates. So you can use 2 light gates to get a start and a final value for velocity, and you might use something like an interrupt card in order to do that. There's also a method where you can use a single light gate and you can use a double interrupt card, but this really depends upon the kit that you have in your school, what kind of light gates you might have, and the sensors and how they're actually working. And then I suppose the fourth method in the guide here is actually using an acoustic stopwatch. Now this is just a stopwatch that turns on with a sound and turns off with a sound. This one is from Freefall, and basically if you have a weight that's underneath the balloon, you can pop the balloon, which makes the starting sound that starts the stopwatch, and then when that weight hits the ground, it's going to make another loud bang that's going to be the thing that actually stops the timer. So you can see that the physics behind this is identical to if you use the falling ball method. We're just using a different way to start and stop that timer. So there's a few different approaches there, but I just want to go through this setup, which is kind of the standard setup, in a bit more detail. This is actually just using, well, a normal kind of retort stand, and I'm going to clamp it onto the desk, and that's just going to hold it nice and firm. And the reason for that is that this method here, with this equipment, uses a plate that has a vibration sensor inside it. So it's not a trapdoor that opens, but it's this plate from the cells, and they lent me the equipment to make this video. But I'm actually thinking it's a really good piece of equipment, so it's something I'll definitely use in my day-to-day teaching. Now, depending on what your school has available, sometimes you might have an electromagnet at the top, and when you turn off the electricity, that starts the timer and it allows the ball to fall. This one is just a simple clip, and I've got a couple of bits of metal that make contact with that metal ball bearing. Now for this, this is going to be the thing that starts the timer, and this is going to be the sensor that stops the timer at the bottom, so we can get a really good value for the time. And this this timer here is the Lascelles millisecond timer. Now there are two different modes. The one we're going to go for with this is mode 2, and this means that gate 1 is going to be the starting thing, and gate 2 is going to be the thing that stops the timer. Probably not the most technical language, is it? So what I'm going to do is take a couple of these leads, going to connect them to the top, and these are both going to go into the thing where it says gate 1. Okay, so we've got gate 1 connected, and then I'm going to put a couple more leads into the 2 connections at the bottom of this piece of apparatus, and they're both going to go into gate 2. Okay, so that's the setup, and then all we need to do is turn it on, and then to actually use it, all you need to do is open the clip, the ball will fall, and then we can record a time. You can then put the ball back into position, you can reset it, and then do the same thing again and again and again. Now of course there might be some limitations to the current setup. It might be that with the height of this retort stand we don't get a big enough range of readings, and therefore students can think about how they can overcome this, perhaps using a taller retort stand, or maybe having this bottom pad on the floor so you can have a much bigger range of readings for height that it falls through. And of course it's good practice then for the students to see how this can be related to a straight line graph where the gradient actually means something. And if you were to plot the height that the ball has fallen through against t squared over 2 on the x-axis, that means the gradient is then equal to the acceleration due to freefall. So this is just one approach, and of course whatever your school has is going to determine exactly how you actually carry the experiment. And obviously some schools, well most schools, are not going to have more than one piece of equipment. So it might be that some students are doing it with this, they can compare it to other groups who might just be dropping a ball through different heights and timing it with a stopwatch. And I think it's really interesting to kind of compare the different methods and the approach that students can take when they know the answer that they're trying to find out. They know they're trying to get 9.81. And therefore, if their answer is wildly different, can the students identify any errors? Is that due to their measurements they're taking, or is there some other kind of systematic error that they haven't accounted for? So yeah, that's just a brief overview of how you can carry out the experiment where you're measuring the acceleration due to gravity.